So good evening all. I'm Pramod Kaval, TA of this course. So I'm going to take a problem solving session 8 on 8 chapters reactor design for the multiple reaction. The course tutor is Professor Vishwada Mandal's Chemical Engineering Department, IIT Guwahati. So I hope that you have gone through the uh, valuable lectures. So based on that, I'm going to take some problems. So starting from the MCQ, for a liquid phase parallel reaction, A gives R and their rate equation given K1 Cs square and activation energy given 80 kilojoule per mole. And second reaction A gives Is with rate equations given and activation energy given 120 kilojoule per mole. The desired product is R. The higher selectivity of R will be achieved if the reaction is conducted at the option are given low temperature in CSTR, high temperature in CSTR, and low temperature in PFR, and is high temperature is PFR. So, so here rate R by RES, K1 by K2 by 2C into K naught reactor by RT, right? K naught is RT, right? So, so S to the power E2 minus E1, right? Divided by RT into C. So here E1 is less than E2, right? So at low temperatures, right? That this the RS rate of R and divided by rate of S is more, right? Is more. Hence we get the more uh, uh, rate of R and rate of S. So we should have low temperature and low temperature and high CA, right? So to maintain the high CA, the PFR is required. So option C is next. So it is a K1, K2, K2, and K1. Here is a statement for a series of reaction A gives B, B gives C. Having K1 less than K2, the reaction system can be approximated as. So here K2 is greater than K1, right? So we will not able to detect the species of B in the reactor at any point in the time. So K1 here, K1 is too small compared to the K1, and any small amount of B form at bomb is instantaneously transferred into the C, right? Because the second reaction gives C is a rapid. This is the series reaction. A gives B gives C could be approximated at B. Sorry, that's the K1. Right. So the lowest step that determines the overall rate and order a reaction in the multiple reaction system. So option D is correct. I move to the question number 3. The reactant R forms three products XYZ irreversibly as shown below. Here is a reaction given. R gives X, Y, and Z. The reaction rate are given by Rx is equal to Kxcr, Ry is equal to Kyc, R raised to the power 1.5, and Rz is equal to Kz Cr. The activation energy for the formation of XYZ are 40 and 5 kilojoule per mole respectively. The pre-exponential factors for all reaction are nearly same. The desired condition for the maximize the yield of XR. The option given: high temperature, high concentration R; high temperature, low concentration R; low temperature, high concentration R; and low temperature, low concentration R. So since here E1 and T22 are equal, so E1 greater than E3, right? The first, second, and third. So X is a desired product. So we go for the high temperature operation. This is following the rule that the high temperature favors the reaction with a larger activation energy. Right. Now there is a competition between the X and Y as we are operating the reactor at a high temperature. So in order to get the maximum yield of X, we need to manipulate and control the variables, the concentration of our reactants. Now let's consider the rate of formation of X and Y. Rx, Ry equal to Kx, Cr,
जैसे प्यार नहीं किया
Ky equal to R 1.5,
वो पढ़ाया हुआ आया था
1 by.
कल के क्वेश्चन है
Learner, kindly mute your mic.
एक आया था
Raju, please mute your mic. So we cancel out Kx, Ky due to here mention that pre-exponential factors, all reaction are nearly same. The activation energy are the same since we assume that the isothermal operating condition are being maintained. Hence, high temperature and low concentration are high temperature and low concentration of R,
इसका
right,
मुझे आइडिया
will be
मैं देख
maximize the yield of the X. Raju, please
इसको
mute your mic.
है ना पढ़ लूँ फिर मेरा आज कंसंट्रेशन नहीं होता
option B is
मेरे को शुगर बता दीजिए डॉक्टर ने मैं दिमाग खराब
moving to the question number 4. Consider the reaction scheme shown below. It gives B gives C. Both the reaction are the first order. The activation energy for the K1 and K2 are given 80 and 120, 20 kilojoule per mole respectively. To maximize the yield of B, it is preferable to the use. Option given CSTR and high temperature, PFR and high temperature, C CSTR and low temperature, and D CSTR and low temperature. So for a series reaction, PFR is usually preferred than the CSTR. So we know that PFR always remains smaller time than does the CSTR to achieve the maximum concentration of B. Right. So also we have note that the high temperature favors the reaction of higher activation energy, right? And low temperature favor the reaction of lower activation energy, right? So here E1 greater than E2, right? So in this case, high temperature will be favor for the reaction A. High temperatures will be favor for the reaction A A1 C, right? So, so to maximize the B, so PFR and high temperature is preferable. Now, question number 5, the variation of the concentration Ca, Cr and Cs for the three species Ar and S with time in a isothermal homogeneous batch reactor are shown in below. Here is a graph given concentration versus time. Select the reactions scheme that correctly represent the above plot. The numbers in the reaction scheme shown below represent the first order rate constant in unit of second inverse. Option given here. So based on that plot, we have to find out the reactions. So by looking the curve CA, we can say that A is A is continuously consumed. Right. Now, if R is found in reversible fashion, so option first we go with option A, and S is found irreversibly. Both are at the same rate. Here is a one same rate. Here is a one indicate the rate. Here three also indicate the rate. Then the curve for S would be the above the curve for R become a more amount of S is formed. Now check the option B. The if both R and S form reversibly with the speed 3, 1 by S and 1 by S respectively. As per the option B, then the curve R would be the above the curve for the S because more amount of R is formed. Hence option A and B are not possible because they show the formation of A via reversible reaction. Now since CR and CS curve merge with each other here, the only possibility is that both the R and S are formed at the same rate. So yes, hence option C is correct. Now moving to the question number 6, consider the following elementary reaction network. So A gives B, B gives D, and A gives C, and C gives D. So you 1, 2, 3, 4. The activation energy for the individual reaction are even 100 kilojoule per mole, E2 150 kilojoule or more, E3 100 kilojoule per mole, and E4 200 kilojoule per mole. If the feed is pure and the desired product is C, then the desired temperature profile in plug flow reactor in the direction of flow should be. So in this question, reaction means reaction network given and then their activation energy given. So the question is, the if the feed is pure, the desired product is C, then the desired temperature profile in the plug flow reactor in the direction of the flow. Here is the direction of flow. Option given: constant at low temperature, constant at high temperature, increasing and decreasing. So from the given data, E1 less than E2 less than E3. Here is a C is a desired product. Right. Now RB directly proportional to RT, right? And RC directly proportional to the exponential E2, RT, right? Now take RC by RB, E1 by E2 by RT, right? Now since here E2 is greater than the E1, so we start at a high temperature so that RC is more than, so E2 greater than E1. So start the high temperatures to start so that the RC is more than RB. Right. So here E2 is RD by RC proportionally E2 4 by RT. So E2 is less than E4, right? So to reduce the RD in comparison to RC, we need to reduce the temperatures. So to reduce the RD in comparison RC, we need to reduce the temperatures. So once a substantial amount of C is produced, it may react a way to give D at a higher temperature. So at this point, we need to decrease the temperature of operation. Hence, a falling temperature is preferred to maximize the production of the C. So option D is correct. So temperature profile in plug flow reactor in the direction of flow should be a decreasing. Now moving to the question number 7, determine the level of CA0 high low intermediate temperature profile, high low increasing decreasing, which will favors the formation of desired product indicate in the reaction scheme is given below. A gives R gives S desired. In second, A gives U. So here is a N1 here with activation energy given. So how to determine the level of Ca and temperature profile. Right. So here yes is a desired product. Right. This is a desired product. We would like to progress in the A, use R, use S route rather than the A gives a U. So since here E1 less than E2, so start the reaction at the lower temperatures. Since low temperature favors the reaction with a lower activation energy until we reach the time when the substantial amount of R is produced. After this point, we need to increase the temperature since R is yes. As E3 45 greater than E1 25, right? So yes, we must have the increasing the temperature profile. When it comes to the concentration, it is evident and we need to maintain the high C inside the reactor. So maximize the production of the yes. So PFR will be the better choice. So since A gives R, a second order reactions and R tends to the yes, since R gives yes, is a third order reaction. Right. So we have to go for the higher C now. The option is high CA, increasing temperature and plug for reactor. Now moving to the question number 8. The methane streams are fed to the reactor in a molar ratio 1 is to 2. The following reaction takes place. The reaction given CH4 plus twice is 2O gives CO2 plus 4 is 2. And CH4 plus is 2 gives CO plus 3 is 2. Where CO is the desired product and CO is the desired product. And H is a H2 is a byproduct. The existing has the following composition. Here is the exist uh, component given with their mole percentage given. So you have to calculate the first selectivity for the desired product related to the undesired. Then fractional yield of the CO2. And third is the fractional conversion of the methane. To calculate the selectivity, there is a formula moles of desired product form moles of desired product form divided by moles of undesired product form. Undesired, right. This moles of CO2 forms, moles of CO2 form divided by moles of CO form. So here CO2 forms 15.2. So here is a mention that CO2 is a desired product and CO is a undesired. And CO is 2.17 equal to 7. Right. So 7 is a selectivity. Now second, fractional yield of the CO2. Here is the moles of the where fractional yield is defined as the ratio of moles of the desired product formed to the moles of that would have been formed if there were no side reaction and limiting reactant had reacted completely. Right. So to estimate the value of denominator of the above equation in this one, we need to know the amount of CH4 present in the feeds. So reaction one, so amount of CH4 consumed equal to amount of CO form is to 1:1 ratio. CO form equal to 15.21 mole. Now reaction two, amount of CH4 consumed equal to amount of CO form. CO form equal to 2.17 mole. 1:1 ratio. Now amount of CH4 unreacted equal to 4.35. Now amount of CH4 in a feed in a feed equal to 15.21 plus 2.17 plus 4.35 equal to 21.7. So there are the no side reaction and CH4 has reacted completely. So we could have got a 21.73 mole of CO2. So fractional yield equal to moles of CO2 forms 15.21 divided by moles of CO2 that would have been formed if there is no side reaction and CH4 had been reacted immediately. So this is 21.73 into 0.7. Now third, the fractional conversion of the methane. So to calculate the fractional conversion methanes, the formula moles of CH4 consumed divided by moles of CH4 initially present. CH4 consumed divided by moles of CH4 initially present. Okay. So 15.21 plus 2.17 initially 21.73. So 0.8. Right. The fractional conversion of methane is a 0.8. So I covered all the questions based on the 8 chapters. So thank you all. We will meet on next Friday on next chapters.